Hello and welcome to the Core Pure 1 video on complex numbers, calculations and solving quadratics. So looking at the information given in the booklet, we've got the definition of I as being the square root of -1. So that is the definition of our imaginary number I. So it follows a fairly straightforward way from that I squared is -1, I cubed multiply this by I is going to be -I, and I to the fourth is 1. So we often write complex numbers as the letter Z, with Z being x plus yi. X is called the real part of the number, and y is the imaginary part. So in this complex number here, we might say Z is 4 plus 3i. This is the real part, and this is the complex part here. Now, I beg your pardon, this is the imaginary part of the number. The whole number is a complex number. So we need to learn the rules, the 4 rules of complex numbers. So how do you add complex numbers? You simply add together the real parts and you add together the imaginary parts. So we've got 2 plus 4 is 6. And we've got 3 minus 7i is 3i minus 7i is going to be minus 4i. And that's our answer there. Just be a little bit careful when you're subtracting, especially if there's a negative number of i's in the second number. So we've got 2 take away 4 is -2 for the real part. For the complex part, for the imaginary part, we've got 3 minus 7i. So that's going to be plus 10i. Now, when we are multiplying two complex numbers together, we just multiply as though we're multiplying out of brackets. So we've got 2 times 4 is 8. And then we're going to do the end terms because that's going to give us another real number. So we've got 3 times -7 is -21. But then I times I is -1. So this whole thing here becomes 20 plus 21. Then the I terms, we've got 12i there. Minus 14i, and then we tidy that up, so we've got 29 minus 2i, and that's the answer to that multiplication. This result here is important. We've got 2 plus 3i multiplied by 2 minus 3i. This is like the difference of 2 squares, so we get 2 times 2 is 4. We're going to get, if you think of the imaginary parts, we're going to get plus 6i minus 6i, so there's going to be no imaginary part to this number. So then what happens with the final term? We're going to have 9, it's going to be -9 multiplied by -1, so that's going to be plus 9, and that's 13. So that's an important result that's reinforced here, that a plus ib multiplied by a minus ib will be a squared plus b squared, and that's a real number. Very similar to rationalizing surds. We use this fact to divide numbers. So if we want to divide two numbers like this, the way to think of doing this is to multiply the top and the bottom of this by 4 plus 7i over 4 plus 7i, just like when you rationalize a surd. And what you get when you do this is, for the top of this bracket, these two brackets, if you like, multiply them together, you're going to get 8. So this is the question that we've done up here. Not quite, actually. No, so we're going to get 8 plus 21i. Sorry, plus 21. Then we're going to get minus 12i plus 14i. And on the bottom, we're just going to get 4 squared, which is 16, plus 49. So tidying all of that up, we end up with 29 minus 2i, and that is plus 2i, and that's over 65. And that is a division because we've got rid of the complex number on the bottom of the fraction. Now, for questions 6 and 7 on this sheet, we're going to use the fact that if two complex numbers are equal, then the real parts are equal and the imaginary parts are equal. And that's a very important result. So if we look at this example here, we're told that x and y are real numbers. So when I multiply this out and equate the real parts, so I'm going to look first of all at the real parts, and you can write real parts like that. So we've got x multiplied by 1, and we've got y multiplied by 1, and that must be equal to 5, because the real parts on the left-hand side must be equal to the real parts on the right-hand side. If we look at the imaginary parts here, we've got minus 2x multiplied by I, and we've got y lots of I there, that must be equal to 8. So I'm then going to subtract these two equations. I've got simultaneous equations. So if I subtract these two equations, I get x minus 2x is 3x is equal to minus 3. So x is minus 1. And if x is minus 1, y is equal to 6. This last question here uses the notation for a complex conjugate. So z star, if we want a complex conjugate of a number, let's have a look up here. If we've got 4 plus 3i, then if I want to think what z star is, that's going to be 4 minus 3i, because complex numbers often occur in these sort of pairs. So if we look at this here, we're going to let z be equal to x plus iy. So then we fill out this equation here, and we've got x plus iy plus 2 times the conjugate, so that's 2 times x minus 2iy minus 2 times the conjugate is equal to 3 minus 4i. And from this, we are going to compare the real and the imaginary parts. So if we look at the real parts of this equation, I've got x and 2x there. So I've got 3x is equal to 3. So that tells me that x is equal to 1. The imaginary parts, I've got y minus 2. So I've got minus y must be equal to minus 4. So y is equal to 4. On to the next page. This is where complex numbers, you would probably have first realized that you needed to be able to use complex numbers. So if we're looking at solving quadratics, it says, first of all, show that z, which is minus 1 minus 2i, is a solution of this quadratic equation. So you could do this by using the quadratic formula. So I'm going to give 3 different ways of doing this. By using the quadratic formula here, I could say z is equal to minus b, so that's minus 2, plus or minus the square root of b squared, which is 4, minus 4 multiplied by a multiplied by c, all over 2a. So z is equal to minus 2. Now, what have we got here? We've got minus 16. So minus 16 square rooted is going to be plus or minus 4i, because that's going to be, take the 16 out and square root it, that gives me 4. That leaves me with the square root of minus 1, which is I, all over 2. And that's equal to minus 1 plus or minus 2i. So we've shown that, we've actually found both the solutions here, but we've shown that that is certainly a solution. So that's one way of doing it. Another method that you could use is you could actually put this into this equation. So you could work out minus 1 minus 2i, square it, and you could do 2 times minus 1 minus 2i and add 5. And you could work out what each of these little parts was equal to. So for this, you'd get 1 plus 4i squared plus 4i minus 2 minus 4i plus 5. And when you work out what all of that's equal to, you get 0 plus 0. So it is equal to 0. So yes, it's a solution. The third way you could do this is you could complete the square for this equation instead of using the quadratic formula. And that would also give you the solution minus 1 minus 2i. We'll do that in the question 3 here. Right, question 2. If you know one root of a quadratic equation, then straight away you know the other root, because you can see from the quadratic formula the plus or minus is always going to generate the second root. So if one root here, if we've got that one root is 3 plus root 3i over 6, then the other root will be 3 minus root 3i over 6. And that's, you can just write that down each time. So if you've got one root is a plus I times b, then the other root will be a minus ib. Right, then this last question, use completing the square to find the two complex roots. So we've got z squared minus 6z plus 10, and we're going to complete the square for that. So it's going to be z minus 3 squared minus 9 plus 10, which is equal to z minus 3 squared plus 1. And we want to find the roots of that, so then we're saying z minus 3 squared plus 1 is equal to 0. Z minus 3 squared is equal to minus 1. We're going to square it by both sides, so z minus 3 is plus or minus, and that's important here, the square root of minus 1, which is plus or minus I. So we've then got z is equal to 3 plus or minus I. I think if this was an exam question and I was asked to do this, I might then split it and say z is 3 plus I and z is 3 minus I, just to be absolutely clear.